In this video, we're going to learn not only the mechanics of how to balance chemical reactions, but also the theory behind why chemical reactions require balancing in the first place. Now, to start with this theory, we need to do a review of what exactly the definition of matter is in chemistry, which is any substance in the universe that has mass and occupies volume in 3D space is defined as matter. Now, the reason why chemical reactions require balancing is because of the nature of matter itself, namely that new matter cannot be created, nor can it be destroyed. It can only be converted from one form to another, which is exactly what we see in chemical reactions. Now, when we apply this phenomenon to a chemical reaction, this means that if we look at the total mass of all of the reactants in a chemical reaction, meaning all of the substances before the chemical reaction has taken place, this must be equal to the total mass of the products, meaning all of these substances that exist after the chemical reaction has taken place. And if no new matter has been created or destroyed, the mass of our products and reactants therefore must be equal. Now, in practice, the way that we ensure this is we do what we call chemical reaction balancing in order to help us obey this phenomenon, which is what we call the law of conservation of matter, which again is just a long-winded way to say that during a chemical reaction, no new substances or no new matter can be created, nor can it be destroyed. Now, the problem is when we're balancing chemical reactions in the abstract, we don't have a way to measure exactly what the mass of our reactants and our products are. So in order to balance the mass when looking at written chemical reactions like this, we simply need to count the number of individual atoms that exist in the reactants, and then do the same for the number of individual atoms in the products, and if those are equal, then we will have fulfilled the law of conservation of matter. So if we try this with this double displacement reaction, we can see that there are 2 chlorines in the reactants, but we only have 1 chlorine in the products here. Likewise, we have 2 sodium in the reactants, but only 1 sodium in the products here, which means that our reaction is not balanced. Now, the only way that we can actually balance this chemical reaction is by adding what we call balancing coefficients before each of the reactants or products in order to change either the number of an individual element or to change the number of all of the atoms within the compound themselves. So we can see that we can only add balancing coefficients before each of the compounds, otherwise we'll end up changing the chemical formula. So if we want to make sure that we have 2 sodium and 2 chlorine in the products to match the 2 chlorine and the 2 sodium in the reactants, we can put a balancing coefficient of 2 right here. And because sodium chloride is the whole compound, this balancing coefficient of 2 applies to the sodium and to the chlorine. Now, if we actually check all of the remaining atoms, we have 1 calcium in the reactants, 1 calcium in the products, and if we group sulfate as a polyatomic ion together, we have 1 sulfate in the reactants and 1 sulfate in the products, and our balancing is actually done because now the reactants and the products each have the same number of individual atoms, and therefore we have obeyed the law of conservation of matter. If we take a look at the example below, we can see that we actually have an ionic compound, aluminum chloride, that is decomposing into individual ions. So sometimes when we balance, we also need to consider the charge. So in this case, what we need to do is we need to make sure that the amount of positive and the amount of negative charges also remains equal. So in this case, we need to make sure that the amount of positive and negative charges in the reactants and the products remain the same. So in this case, aluminum chloride, the ionic compound, actually has no charge here, meaning that we need a total charge of 0 in our products here. Well, we can actually fix this just by balancing the number of chlorine atoms. So we've got 3 chlorine atoms in the reactants, and therefore we can add a balancing coefficient of 3 in front of the chlorine ion here. And because we only have 1 aluminum ion, that means we have 1 aluminum ion with a charge of positive 3, and 3 chlorine ions, each with a charge of negative 1, and negative 1 times 3 is negative 3. Positive 3 minus 3 is 0, and we can see that the total charge of our reactants and products, as well as the number of individual atoms, is also the same. So we can see that we've balanced both charge and the number of atoms. Finally, one of the other details that you will notice in the chemical reaction is subscript that is listed after each of the individual reactants and products. And this is what we call the state of matter of each of our reactants and products. And if this is labeled as S, this would be a solid. So this would tell us that our reactant or product is in the solid form. If it is labeled as L, this would mean liquid. If it is labeled as G, this would mean that the compound or element is a gas. And finally, 3 of the 4 substances in this reaction are labeled as AQ, which is the short form for aqueous, which is not actually the same as liquid. Aqueous is a word that means that it is dissolved in water, meaning that we're working with some sort of solution here. So once our chemical reaction is balanced in terms of each individual atom in the reactants and the products being equal, once all of our substances are labeled with a proper state of matter, we have finished balancing the chemical reaction. To test your knowledge of balancing, you can take a look at the practice problems below and see if you can balance these chemical reactions. And in the next video, we're going to go over a few key strategies that can be used to balance more complicated chemical reactions.